Hello all, welcome back. Today we'll be continuing with our nozzle characteristics. So continuing to your next, that is, we'll discuss regarding the thrust as well as the thrust coefficient. Now, what do you mean by thrust is basically the efflux of propellant gas. It is the momentum that is being flowing out which causes thrust. That is nothing but a simple reaction force of a rocket structure. Now, because the flow is supersonic, the pressure at the exit plane of the nozzle, which may differ from the ambient pressure, and a pressure component in the thrust equation adds or subtract to the momentum thrust that is given by this form, right? And where this is my pressure component and this is with respect to my momentum, and F will be my thrust. Now, the maximum thrust of any given nozzle operation is to be found where P3 equals to 0, that is P ambient equals to 0, right? And between sea level and a vacuum of space, the equation that we have discussed earlier gives the variation of thrust with altitude, and applying the properties of the atmosphere, a typical variation of thrust with the altitude from a choked nozzle where mass flow rate is equals to 1. Similarly, or the mass flow rate is maximum and would be represented by a smooth increasing curving to an asymptotic value. And to modify the values that are being calculated for an operating condition, that is P2 to P3 or P at a nozzle exit equals to P of ambient, and for other conditions whereas P1, K as well as epsilon can be used as for the thrust, it can be rewritten in this form, whereas F optimum or the optimal thrust to the pressure differential, as well as in order to get my specific impulse, optimal specific impulse to a value of this pressure component. Now, the specific impulse at a new exit pressure, that is P2, corresponding to the new area ratio, that is A2 by A2, AT, area of throat, is to be calculated, and the relations that we have discussed are to be used. And the equation can be modified by substituting V2, Vt and Vt using force values, right, in order to guess this equation. Now, the first version, that is this equation, is general and applies to the gas expansion of all rocket propulsion systems. The second form, which applies to an ideal rocket propulsion system where K, that is the gas constant, being constant throughout the expansion process. This equation shows the thrust which is proportional to the throat area AT and the chamber pressure or the nozzle inlet pressure P1, and is a function of pressure ratio of the nozzle, that is P1 is to P2, the specific heat ratio K, and of the pressure thrust. The equation that we have derived earlier, this equation is called an ideal thrust equation. Now, coming to thrust coefficient, CF, denoted by CF, is now defined as thrust. It is divided to the value of chamber pressure, that is P1, and the throat area, right, which can be rewritten in terms of force, that is the thrust generated, into the pressure at the chamber and the area of the throat, which can be rewritten in form of this. Now, the thrust coefficient C suffix F is dimensionless, and it's a key parameter for analysis and depends on the gas property like K and a nozzle area ratio epsilon. The pressure ratio across the nozzle, that is P1 to the P2, but it is not directly dependent on the chamber temperature. For any fixed ratio, that is P1 to the ratio of P3, that is P1 chamber to the ambient, the thrust coefficient, particularly CF, and the thrust F have a peak of P2 equals to P3, as the area ratio epsilon varies. The peak value is known as the optimum thrust coefficient, and it's an important criteria in nozzle design. the introduction of the thrust coefficient permits in the following form, that is F equals to CF AT into P1, where CF is my thrust coefficient, AT is the area of throat, and P1 is my chamber pressure. Now the equation for solving CF to experimentally determine the thrust coefficient from the measured values of chamber pressure, throat diameter as well as the thrust. Even though the thrust coefficient is a function of the chamber pressure, it is not simply proportional to P1. However, it is directly proportional to the throat area. The thrust coefficient, which has a values ranging right from under 1 to roughly 2, and the thrust coefficient may be of representing the amplification of thrust due to the gas expansion in the supersonic nozzle as compared to the thrust that would be exerted if the chamber pressure acted over the throat area only. Now, in a convenient parameter, the visualizing effects of the chamber pressure or the altitude variations can be given in nozzle configuration, and for modifying sea level results to flight conditions. Let us go through a small graph to understand where we will be plotting with respect to the thrust coefficient to the pressure ratios. Pressure ratios, particularly the combustion pressure, that is denoted by P1, and the throat pressure, that is P2. Next, now, and a specific heat ratio for optimum expansion, what we are considering is P2 equals to P3. Now, for specific area ratios, let's say for epsilon and a K values of 1.1 to 1.4, we can observe that as the pressure ratio, right, as the pressure ratio increases, we can see the thrust coefficient also increases. But in relation, as the K increases, K decreases, the pressure ratio increases, the thrust coefficient also decreases, right? And where these vertical or horizontal line which are crossing are my area ratios. As we keep on increasing the area ratio proportionately, right, the area ratio increase and increase in the K value, that is gas constant, and increase in pressure value, the overall increase of CF, that is the thrust coefficient, happens, but at a marginal value. Now, coming to this, the thrust coefficient, that is particularly CF versus the nozzle area ratio for K equals to 1.2. What we are getting out of this is we are understanding the maximum amount of flow that can occur in a nozzle completely. So the thrust coefficient to the area ratio, that is A to exit area to the throat area, and a supersonic. Right? Now, under this, what we are having for different pressure ratios, that is P1 to P3, that is chamber pressure to ambient pressure. Right? The ratio of chamber pressure to ambient pressure with the maximum value of 2.26 for a certain area or certain K value that we are limiting up, which shows the different regions within which the flow separation or the flow separation occurs, right? So as the area ratio increases, right, although the thrust coefficient, that is CF, increases for a particular region, let's consider for a point 10 or pressure ratio of 10, what happens for an area ratio of approximately somewhere around between 1 to 1.5, right? What happens? You are getting a maximum amount of thrust coefficient. Sorry, just a second. Right? Now, that upon considering the max value, what you are getting? A line which is giving us the optimum thrust coefficient. And few times, particularly as the thrust coefficient decreases, there will be a region where the flow separation occurs, and that is unavoidable. But there is an intermediate region where we can proportionately change to incipient the flow separation. Now, next will be the thrust coefficient versus the nozzle versus ratio for K value of 1.3. Considering the same, the area ratios to the thrust coefficient, if you are considering for the same area ratio of 10, the pressure ratio of 10 for the area ratio, what you have initially for a lower region, you will be having what? The flow separation, right? As soon as the pressure increases, right, and the area ratio decreases, a specific point, particularly this, will give you an optimal thrust coefficient. Now, these set of curves, which are very useful in examining a nozzle problems, if they permit the valuation of under as well as overexpanded nozzle operation. The values given in these figures are ideal and do not consider such losses such as divergence, friction as well as internal expansion waves. When P1 to the P3 becomes very large, particularly the expansions near vacuum, the thrust coefficient approaches asymptotic maximum, that is shown for K 1.2 as 1.3 in my previous graphs. Now, these figures give the value of CF, that is thrust coefficient, for some mismatched nozzle condition for cases where P2 is not equal to P3, provided that the nozzle is flowing full at all times. The working fluid does not separate or break away from the nozzle walls. Now, a characteristic velocity, the next component for nozzle characteristic, is defined as characteristic velocity or specific impulse. Now, the characteristic velocity, that is C star, was defined earlier and which can also be shown as in this form, where P1 is my chamber pressure, AT is my area of throat, and M dot is my mass flow rate, which in terms of can be rewritten in terms of rocketry, specific impulse, gravitational constant, and thrust coefficient. Now, this velocity is not only a function of propellant characteristics as well as combustion chamber propellant properties, it is independent of nozzle characteristics. Thus, it can be used to figure a merit comparing different propellant combinations for combustion chamber performance. Now, the first version of the equation that we had explained earlier also applies in general and allows determination of C star from an experimental approach of values of mass flow rate, chamber pressure as well as throat area, and the last version gives us an ideal value of C star as a function of working gas properties, namely K, chamber temperature as well as effective molecular mass. The term C star, particularly C efficiency, characteristic velocity, can be used to express the decrease of completion of chemical energy, right, releases in the generation of high temperature, high pressure gases in combustion chambers. Now, it is a ratio of an actual value, particularly C star, as determined from measurements, to the theoretical value, has a typical values that are ranging between 92 to 99.5, whereas the combination of both equations, which allows us to express the thrust itself as a mass flow rate times the function of combustion chamber parameters, a function of nozzle expansion ratios, namely in this form, right? Some use a term called a discharge coefficient, C suffix D, which is namely a reciprocal of our characteristic velocity. Now, both CD as well as the characteristic exhaust velocity can be used only for chemical rocket propulsion systems, and the influence of the variations in specific heat ratios K on the various quantities such as C, C star, area ratios, velocity ratios as well as specific impulse is not as large as those from changes in temperature, pressure ratio as well as the molecular mass. And for value of 1.67, which is for monoatomic gases such as helium or argon, and 1.4 for a cold diatomic gases such as hydrogen, oxygen as well as nitrogen, and for triatomic or beyond varies from 1.1 to 1.3. For example, methane has a 1.1 and ammonia as well as carbon dioxide are with 1.33. Now, in general, the more the complex the molecule, the lower the value of K. This is also true for molecules at high temperatures when their vibrational modes have been activated. And the average values of K, that is gas constant, as well as the molecular mass for a typical rocket exhaust gases with several constituents depend strongly on the composition of the products of combustion, particularly chemical constituents and their concentrations. Now, coming to our next topic in understanding the nozzle characteristics, we will be going through the under as well as over expanded nozzles. An under expanded nozzle discharges the gases at the exit pressure greater than the external pressure because the exit area is too small for an optimal expansion. What is our case for optimal expansion? Is nothing but P2, that is the exhaust pressure, should be equals to my ambient pressure. Now, a gas expansion is therefore incomplete within a nozzle, and a further expansion will take place outside the nozzle exit because the nozzle exit pressure is higher than the local atmospheric pressure. And in an over-expanded nozzle, the gas exits the lower pressure than the atmosphere as it discharges area too large for optimum. And the phenomenon for overexpansion inside the supersonic nozzle is indicated schematically in a figure that we will be discussing further from a typical early pressure measurements of superheated steam along with nozzle axis as well as different back pressure or pressure ratios. Now, let's see a graph which shows the small in what way the underexpanded as well as the overexpanded nozzles are formed or can be identified. Now, the figure shows the distribution of pressures in a CD nozzle with different flow conditions where the inlet pressure is the same as well as the exit pressure changes. Now, this is my CD nozzle and this will be my throat. Right? What happens on the CD nozzle or the convergent part of the nozzle? Right? And let's consider the curve A. A is my starting point from which the combustion pressure, that is P1, starts, and P2 is my throat pressure. Right? Now, what happens under this? Now, as coming as a fluid, particularly the gases are moving from point A, that is from combustion chamber inlet to my throat. What happens? The pressure drops. Right? Now, under this case, what happens? We are having multiple curves. We will discuss one by one. We'll start with B. Right? If the pressure curve is going smoothly towards B, right? What happens? It is under optimal expansion where the expansion, particularly P2 equals to P3 or PA, right? Now, if the external expansion waves at a high altitude are formed at optimal expansion. Now, as the altitude decreases, right, or as the pressure decreases, what happens? It goes up. Like the supersonic flow that is at the downstream of my divergent nozzle, jet separation as well as internal oblique shocks inside the divergent section will occur, right? If these are not equal, let me just rewrite. Right? If they are not equal, what happens? The separation, it means if in case P2 is greater than PA or P2 is less than PA, any case, right? What happens? If P2 is greater than PA, at that time the gases that are coming out would tend to expand out, right? Would tend to expand out, putting up the more pressure. Now coming to if P2 is less than PA, At that time, what happens? The flow separations, particularly the jet separation, occurs and it creates an internal oblique shocks. Now, if the pressure is much more lesser at the CD nozzle, at the time the flow converts itself into a subsonic flow. Now, the curve which we have discussed earlier, which shows the pressure variation with an optimum back pressure, which is fully corresponding to the nozzle area ratio, and a curve AC to AH, which shows the pressure variations along the axis for increasingly higher external pressures. And the expansion within the nozzle proceeds normally after its initial portion, that is till the throat. But at any location after I on the curve AD, the pressure is lower than the exit pressure, and a sudden rise in pressure takes place, that is accompanied by separation of flow from the valves. Now, the separation behavior in nozzles is deeply influenced by the presence of compression waves or the shock waves inside the diverging nozzle section, which are strong discontinuities and exist only in supersonic flow. And the sudden pressure rise in the curve ID represents such a compression wave, which we can see here, I to D. Right? Now, the expansion waves which are below point B, also a supersonic phenomena, act to match the flows the nozzle exit at lower ambient pressures. Now, these are different possible flow conditions in a supersonic nozzle, which can be stated as: 1. That is when external pressure P3 is below the nozzle exit pressure P2. Right? The nozzle will flow, but they will be a form of external expansion waves at its exits. Right? For example, as it comes, as there is less pressure out, sorry, this will be P2, this will be P3. As the P2 is bigger than P3, what happens? They tend to move out. Right? And the expansion of the gas inside the nozzle is incomplete, and the values of CF and IS, that is specific impulse, will be less than that of optimal expansion, and for external pressures that are P3 somewhat higher, right, somewhat higher than the nozzle expansion. So for example, P3 is somewhat higher than P2, and the nozzle will continue to be flow full. This will occur until the P2 drops to a value between 10 to 40% of P3. The expansion is somewhat inefficient, and the CF, particularly the thrust coefficient, will have a lower values than the optimum nozzle would have, and a weak oblique shock waves will be developed outside the nozzle exit section. At higher external pressures, the flow separation will begin to take place inside the divergent portion of the nozzle. The diameter of the exiting supersonic jet will be smaller than that of nozzle exit diameter, with steady separation remains typically axially symmetric. Now, the axial location of the separation plane depends on both local pressure as well as the wall contour. The separation point travels upstream with increasing external pressure. At the nozzle exit, the separated flow remains supersonic in center portion, but surrounded with an annular shaped section for the subsonic flow. There is a discontinuity at the separation location, and the thrust is reduced compared to an optimum expansion nozzle at available area ratio. The shock waves that are generated may exist outside of the nozzle in plume. And for nozzles in which exit pressure, that is P3, is just below the value of the inlet pressure P1, right? The pressure ratio is below the critical pressure ratio, and the subsonic flow would prevail throughout the entire nozzle. This condition normally occurs in rocket nozzles for a short time during start as well as stop. The methods for estimating the pressures at a location of the separation plane inside the diverging section of a supersonic nozzle have traditionally been empirical. the actual values of the pressures of an overexpanded as well as underexpanded regimes described are functions of the specific heat ratios as well as the area ratios. Now let us understand this. Given figure shows the thrust coefficient of two nozzles of different area ratios. One has jet separation at about 7,000 meter altitude, which means 7 kilometer altitude. Now the graph which is plotted against the altitude as well as the thrust coefficient, and this will be my CD nozzle and this will be my throat. Now what happens? This is my CD nozzle bell. Now what happens if we'll consider three cases. If P3, P2 is greater than P3, right? So the pressure that is coming out of the nozzle is higher than the P3. What happens at the time? As we discussed earlier, the flow would get out, right? Now what happens if the same P2 is less than P3? At the time, the exit pressure or the atmospheric pressure will tend to pressurize the flow in, right? Now what happens during this? If a contour or a flow, if in case as the altitude happens, as at the sea level, mean sea level, the gases that are being formed are this, because during the start phase. Now as it moves up, particularly as the altitude increases, right, what happens? The atmospheric pressure drops and the pressure that is inside the contour, particularly CD nozzle, increases. At the time, this exhaust plume would tend to move farther from the central axis line to get a final value or the designed value of my flow. Now what will that be? Is nothing but the contour, particularly the flow contour at 7,000 meters or 7 kilometers as the nozzle has been designed. Now what happens during this? Basically, if for a constant area nozzle, particularly the area ratios of 6.0 as well as 15.0, initially there will be a separated flow as we have seen in the figure, right? After at certain altitude, particularly 7,000 meters or 7 kilometers, the flow is not yet being separated, but the flow is flowing along the wall of the CD nozzle, right? So there is no separation. You will be getting some thrust, right? Now the maximum amount of thrust that it can generate is basically this value. Similarly, for an area ratio of 6, what happens? If you are creating a nozzle here only, right? If I am considering this as not my nozzle, if this is my nozzle, bell nozzle, what happens during this? The flow tends to expand from here itself. So you can get more clear amount of thrust from the initial stage itself without any separation flow. Now if there is any variation, right, let's say for example as the altitude increases, we are changing the area ratio to bigger or more further, so that as the altitude increases, we are increasing our area ratio to expand the nozzle, which gives the thrust curve in this form, right? So as the area ratio changes, you will be getting the difference amount of the area or difference amount of thrust coefficient of the same nozzle. As the axial thrust is not usually altered by the separation plane, because the steady flow that tends to separate over a uniform or the divergent portion of the nozzle, but during start as well as stop transient, this separation may be axially symmetric and may momentarily produce large side forces at the nozzle walls. Now, and during the normal sea level transient, particularly large rocket nozzles, before the chamber pressure reaches its full value, some momentary flow oscillations and Non-symmetric separations of the jet flow may occur while in overexpanded flow operations. The magnitude and the direction of these transient forces may change rapidly as well as erratically, because these results in side forces can be large and they have caused failures at a nozzle exit core structures and thrust vector control gimbal actuators. And when a flow separates, as it does in a highly overexpanded nozzle, the thrust coefficient, that is CF, can be estimated only when the location of the separation of the nozzle is known. The CF, that is thrust coefficient, thus determined, relates to an equivalent smaller nozzle with an exit area equal to that at the separation plane. Thus, with the gas flows, a nozzle designed for high altitude, a larger value of E, that is area ratio, could have a larger thrust at a sea level than expected, and in this case the separation may actually be desirable. But the continuous separated flow operation, a large and a usually heavy portion of the nozzle, is being not utilized, making it bulkier and longer than necessary, and such added engine mass and a size decrease flight time as well as its performance. So designers, particularly rocket designers, therefore usually select an area ratio that will not cause a separation. Let us see a small figure. These are the sketches of a gas behavior of three typical type of nozzles of all three launch vehicles. And the first vehicle has the biggest chamber and the high thrust, but the lowest nozzle exit area. And the top as well, or the third stage, usually has the lowest thrust but the highest nozzle exit area. We will see the conditions, right? During sea level or during flight. During sea level, where P ambient is max, whereas and during flight the P ambient decreases gradually over a period of time. Now, where H is my altitude and I is nothing but my specific impulse, AT to area is the area ratio, which is denoted by epsilon. Now we will understand, in a three-stage rocket engine, right, for an area ratio of 6, under sea level, what we are creating, the flow tends to expand as we have designed it for sea level, particularly low level flights. It tends to expand completely or optimum expansion, right? And during flight also the engine will flow full, means it is being designed particularly to operate under atmospheric conditions and with slight under expansion that can be neglected. Now coming to my second stage, right, with an area ratio of 10 and with the on a sea level, what happens under sea level? There will be pressure that is pushing the jet flow inside or towards the center of the nozzle. So what happens? The flow tends to overexpand but slightly contract, means slightly shrink at the exit if you are testing under sea level. Now, as during the flight and at an altitude of 24 kilometers or somewhere else, where the pressure of atmosphere decreases, right? We know as the altitude increases, the pressure decreases. So as there is no less pressure under full complete expansion, what they tend to push out, right? The gases tends to push out the atmospheric air so that you will be getting a curve, particularly an under expanded curve. Now coming to third stage, where it works under a near perfect vacuum. If you are testing out the same engine under sea level, that is particular zero altitude, what happens? The flow separation occurs, which is caused by an overexpansion, where as there is more pressure, the flow tends to shrink a bit, as well as it tends to separate before the nozzle exit area, which causes a separation curve, right? So the whatever the air or particular atmospheric air is there, it tends to move in. Now coming to the same under during flight at 100 kilometer altitude, what happens as there is less air compared to my second stage as well as my first stage, they tend to push more farther out, right? Now what happens to this? Now coming to specific impulse, on comparing with the sea level particularly, the first stage would remain same, the specific impulse generated, because they are designed to operate on ground and near to the Earth's surface. Now, whereas the second stage as well as the third stage, they tend to move, particularly during in-flight, they tend to move. So, as during flight, what happens? The mass of the rocket decreases gradually, so the specific impulse increase compared to my sea level static test, right? Now, because of the potentially uneven flow separation and the destructive side loads, and a sea level static test of an upper stage or of a propulsion system with high area ratios are usually avoided because they result in overexpanded nozzle operation, and instead tests are done on a sea level substitute nozzle, but also called as my stub nozzle. And for atmospheric flights, the rocket systems have to operate over a range of altitudes, and for a fixed chamber pressure, this implies the range of nozzle pressure ratios. And the most desirable nozzle for such application is not necessarily the one that gives the optimum nozzle expansion, but the one that gives the best vehicle overall flight performance, particularly total impulse, range as well as payload. And this can often be related to a time average over the powered flight trajectory, and a continuous optimum performance for an ascending, particularly launch rocket would require a rubber-like diverging section which would lengthen or enlarge itself so that the nozzle exit area, that is A2 would increase as the ambient pressure, that is PA, decreases. And such design would allow then the rocket vehicle to attain its best performance at all the altitudes as it ascends. And as yet we have not achieved such that flexible and stretchable mechanical nozzle designs with full altitude compensation similar to stretching rubber, right? However, there are number of practical nozzle configurations that can be used to alter the nozzle shapes with altitude and obtain peak performance at different altitudes, right? So let us give a small recap over this. Whenever we are on to design of from nozzle, what we are supposed to do is, as we have discussed earlier, as the ambient pressure decreases, the area ratio, particularly epsilon, is supposed to be increases, right? In order to get my optimum flow or expansion ratio. Now coming to this, what happens? Either the nozzle is supposed to be modified either in flight or during static flight in such a way that as the pressure ratio changes, the ambient pressure changes, the area ratio is also needs to be changed to get my optimum flow, right? That can't be done during in-flight because whatever the nozzles we are using, those are fixed type of nozzles, right? So currently a small research work is going on in order to create flexible nozzles. This we will discuss under further to understand what are the types of nozzles that can be implied onto the flexible side. Now, what this type of flexible nozzles are supposed to do is basically compensate the area ratio with respect to my pressure, its ambient pressure, to achieve my optimum expansion ratio. Simple as that, right? Because the two factors, we can't change the ambient pressure, right? Only thing we can change is my area ratio, particularly the nozzle area through which the flow gets expanded. Now, based on that, what I will be doing, I will be creating a nozzle design in such a way that it compensates with respect to the altitude to obtain my peak performance, right? And the next class, what I will be doing is basically the nozzle characteristics for furthermore and discuss regarding the nozzle types that can be used, right? Thank you.
Like, share and subscribe. Hit the bell icon for more updates.